Hello everyone, this is Chenyang Zhao from University of Southern California. Today I'm going to present an isotropic 1.25mm whole-cerebrum pCASL imaging at 70. I have nothing to declare. Arterial spin labeling was thought as one of the most promising techniques that could benefit from ultra-high field MRI for two reasons. First, the inherent SNR gain has a superlinear relationship with the field strength. Second, the blood T1 is longer, about 2 seconds at 70 versus 1.6 seconds at 30. The combined effect is supposed to bring a 3 times higher SNR at 70 compared to 30. However, to take advantage of the 70, we are facing a lot of technical challenges. B1 and B0 field inhomogeneity lead to a low labeling efficiency for pCASL labeling and low inversion efficiency for background suppression, which may lead to up to 50% perfusion signal loss. Also, there is a lack of robust readout sequence because the blood T2 and T2 star are very short. Workhorse sequence 3 degrees and EPI was reported not working well in literatures, and EPI sequence also suffers from a heavy bolt effect. Our approach, which was presented in last year's ISMRM, was proposing optimized pCASL labeling parameters and background suppression pulses to reduce the perfusion signal loss, and we presented a 3D turbo flash pCASL readout sequence showing improved robustness and was capable for 2x2x4mm resolution with whole-cerebrum coverage. In this work, our goal is to further improve the spatial resolution of pCASL imaging with an ultimate goal of achieving CVF mapping at the macrovascular level. The motivation of doing so is that, firstly, ASL is believed to be the most sensitive technique in detecting neural activities. From literature, there is a 40% signal change in CBF during fMRI task, comparing to 1% in BOLD and 5% in CBV. Secondly, human cortex thickness varying from 1.5 to 4.5 mm, and there are 6 neuronal layers. To achieve layer fMRI, higher resolution close to isotropic 1mm or sub-millimeter is desirable to adequately sample the layers and avoid partial volume effect. Now, at 70, it is readily feasible to acquire whole brain, vessel, and BOLD imaging with sub-millimeter resolution. However, pushing the resolution of 70 SL is still limited by aforementioned challenges and is inherently poor SNR. Therefore, we are motivated to believe there is an urgent need for a high-resolution pCASL imaging technique. Towards that goal, we developed a pCASL sequence with isotropic 1.25mm resolution. The FOV is 220 by 200 by 100 mm with 80 slices covering the whole cerebral. The acquisition was accelerated by 4.5 times in both phase and partition directions. In addition to acceleration, segmented readout was deployed to acquire each volume in 10 segments. Labeling duration and post-labeling delay were both 1.5 seconds, and the effective TR varying from 6 to 7 seconds according to the SAR of each subject. We scanned 10 averages in 22 minutes. To further improve the labeling efficiency, we have a phase-cycled pCASL pre-scan to calibrate the phase accrual during the labeling due to B0 inhomogeneity. The sequence diagram below shows our developed sequence in one effective TR. We placed a selective bias before labeling and a non-selective bias during PLD to suppress the tissue signal. This design allows perfusion signal only experience one bias pulse and improve the tissue suppression compared to single bias design. Both bias pulses were optimized from our previous studies. The 3D TFL readout contains 256 TRs of RF spoiled gradient echo, which in total is about 1.2 seconds and acquire signal of a segment. As shown in the figure on the right, each segment was represented by a different color. and the combination of them formed the undersampled K-space. Poisson disk undersampling with variable density from K-space center to peripheral was used. This undersampling produced incoherent aliasing and can be resolved using compressed sensing reconstruction. This slide shows our reconstruction method. Here is the formula for our compressed sensing. The first term enforces the data consistency in the principle of parallel imaging. Matrix UFSC here represents undersampling, Fourier transform, coil sensitivity, and convolution with point spread function. We reconstruct the control and label images at the same time. XC and XL and the BC and BL represent control and label images and acquire K-space data. The following two terms represent the L1 regularization that helps compressed sensing to enforce sparsity. In addition to the sparsity in label and control images, we also enforces the sparsity in perfusion images that can also help improve SNR of perfusion images. Another important consideration in our reconstruction is image deblurring. We realize that there is the signal modulation in K-space, especially in the partition direction, due to the ASL signal decay during readout. Therefore, we simulated this signal decay and calculated the resulted point spread function. The PSF can be converted into a convolution matrix and embedded into our reconstruction algorithm as the operator C. The image reconstruction was implemented using an in-house MATLAB program that employs FISTA and ADMM algorithms. Here is our result from one subject. I'm putting the CBF map side by side to an MP2 ridge image acquired with resolution of 0.9 mm. The CBF maps show excellent anatomical fidelity across axial, sagittal, and coronal views. Sufficient SNR was achieved, and the through-plane blurring was controlled by a proposed reconstruction method. Here I am showing the zoomed CBF maps with the CSF and Y matter boundaries. The detailed delineation of the superior, middle, and inferior frontal cortex, M1 and S1 areas, as well as the frontal and occipital cortex regions and the visual cortex can be clearly seen. Additionally, the coral plexus is distinctly visualized due to the enhanced resolution and image quality. Now I'm going to show the gallery of our scans. This is the first subject. The second subject, the third subject. In total, we have 9 subjects, age ranging from 20 to 60, and 5 males, 4 females. This is our last subject. For the applications, we first try to analyze the depth-dependent CBF profiles. We hand draw 7 ROIs on the MP2 ridge images for the SFC, MFC, AFC, M1, S1, and temporal and occipital areas. And we co-registered the CBF maps to the MP2 ridge images, then extract the CBF values from superficial layer to deep layer in those regions. We found the middle layer generally exhibit the highest CBF across all examined regions, and the superficial layers receive more blood flow than the deeper layers. Notably, the temporal and occipital regions display significantly lower CBF levels compared to others. The rightmost figure, we also mapped the CBF across the cortical surface from the superficial to the deep layer to appreciate the difference of CBF in different cortical depths. Another application we have tried was to analyze the tract-specific CBF values. We collected 70 DTI data with 1.5mm resolution on one subject and generated the tracing of 2 major tract bundles, cortical spinal tract and the corpus callosum tract. We have also calculated fractional anisotropic map from DTI and co-registered it with CBF map. Then we analyzed the FA and CBF values on each fiber. We found that there is an inverse relationship between the FA and the CBF values. To summarize, this study demonstrates the feasibility of 3D TFL pCASL to achieve whole-cerebrum isotropic 1.25mm pCASL imaging. Pulse-on disk undersampling and compressed sensing reconstruction were attempted to improve the image quality. We have shown robust measurement of CBF on 9 subjects, with the potential applications in depth-dependent CBF profiles and tract-specific CBF values. I would like to acknowledge the mentorship of Professor Danny Wang and Yonggang Shi, and thank all lab members from LOFT and the NICR lab at USC. I would like to also thank Samantha Ma from Siemens and the funding support of NIH and resources from Lonnie at USC. Thank you for listening and appreciate your questions and suggestions.